It's already circulated.
Okay. Thank you. Once again, apologies. I was completely caught by surprise. This alumni is my batchmate actually from 2005. So I cannot ignore such things. Okay, can we begin then?
Yes, sir.
Okay, lecture number 16, scribe group number 15, ID number 87,
Yes, sir.
88,
Yes, sir.
89, 90,
Yes, sir.
91,
Yes, sir.
92.
Yes, sir.
Right, so I hope you have got some time out to look at my video. Finished the group theory portion of the course. In case there are no doubts, we can start module 2 today. It's linear algebra. Any sort of big doubts in the proof from the last class? Okay, I don't know. I mean, maybe some of you have not got the time to look at the video. Please do so, and maybe next class, let me know in case there's something that you have not understood. Once again. So this is linear algebra. It is more familiar to all of you, I'm sure. Right? You may have, or you must have solved equations of this kind, right? Linear equations in two variables. Is that right?
Yes.
Yes, sir.
And similarly, of course, also three variables. Yes? Or no?
Yes, sir.
Yes, sir. We have done.
We have done that. Okay. Four variables?
No, sir.
No. So, just for my understanding, because the old, I don't know what is happening these days in schools, just to get some idea what are the things that you're familiar with. So you have all done three equations in three variables, and all of you know how to solve it. Is that right?
Yes, sir.
Yes,
Yes,
sir.
sir.
Right. So there are two things that we'll be looking at in the course to begin with. One is, rather than seeing how to solve this equation, what concerns us in this course is when can we solve these equations. Perhaps till now we have only come across equations, maybe in two or three variables, it doesn't matter, that have a solution. Okay, but it is not necessary for these equations to have a solution. So that is our primary concern, okay, in the first module on linear systems of equations. When will the solution exist? And secondly, we know how to solve two equations or three equations in two or three variables, but in practice, right? For example, if you look at the Google search engine, which is a very famous example, right? Number of equations and number of variables go up to millions and millions. Okay, so in that case, how do we handle such systems? There are several issues, at least three that I can remember. One is, how do you solve, first of all? How do you handle millions of variables? Okay,
Neural
that would
networks.
Sorry?
Neural networks.
No, that's not the answer.
Matrix.
Yes, matrices, that's right. But again, with matrices, see, all of you have computers with maybe 4 GB RAM or 8 GB RAM, right? So there is limitation to the size or dimension of the matrix that your computer can handle. Just think what will happen if you have a, let's say, I don't know, 10 million by 10 million matrix. Will your computer be able to handle such things? Simply the answer is almost always no. Because we are not going to look at sort of practical implementations. We are going to look at general strategies, and maybe later on in your third and fourth year, you will come across methods to handle such huge linear systems. Okay, so that was the first thing, I guess. Second thing is, so as of now, in order to solve three equations in three variables, you require some number of operations, right? Where the operation could be either addition of real numbers or multiplication of real numbers. So that also is important, right? You would want to solve these equations as quickly as possible. You may not see the importance of that if you have a system of only three equations and three variables. As soon as you look at real life systems and you have, let's say, maybe a million equations and million variables, it starts to matter. You cannot wait for 10 minutes in order to get the solution. Okay, you need to come up with efficient algorithms in order to solve these equations. So that's the second important point. Okay. Third is, so in this case, if you look at both these sets of equations that I have given, the coefficients or the numbers that you can see in these equations are all integers, right? In practice, again, whenever you have these linear systems of equations, you may have all sorts of real numbers, maybe square root 2 rather than 2. Okay. Then, what are the issues? You will be implementing or solving these systems on a computer, right? Now, a computer, can it handle square root 2?
No, sir.
Right? You may have gone through this course on digital logic and design, in which you may have seen these floating point representations of numbers on a computer. Okay, so if you have square root 2, the actual system that your computer solves will not be solving the system with square root 2. There will be some round of errors, right? If there are round of errors, so that means you are not solving the original system but a slightly different system of equations. What is the guarantee that by solving a slightly different system of equations, the solution that you will get is close to the solution of the original solution? Okay, at least I'm sure you agree that solution to the new system of equations may not necessarily be the same as the solution of the original system. But if it is very close to the solution of the original system, you can still go by it. But what is the guarantee that the solution of the new system of equations is close to the solution of the old system? That is another very, very important aspect of linear equations that you must keep in mind. Okay, so why I am stating this is because linear system of equations, although usually everyone feels that it's a trivial topic and it's possibly not going to have any real life implications, that is what you think, right? Both of these assumptions or preconceptions are very incorrect. This is still a very active research area, and research is going on that the research is going on all these three aspects. Okay, how to handle huge systems of equations. So typically the word is distributed systems. Okay, so you may have different computers. All these different computers may store different parts of the matrices, and each system may try to come up with a partial solution, and then you want to merge it. That is what is meant by distributed systems. Other thing is how to efficiently solve it. So there are parallel algorithms and other algorithms that exploit the structure of the matrix. And that's the second area of research. Third, rounding of errors. So this is what is called perturbation analysis. So instead of 2, if I sort of perturb this number a little, from 2 I take it to be, let's say, 2.000567. How is this going to impact the solution? Okay, so all these three are very relevant in practice. Okay, whether it is machine learning, data analysis, etc., social network data analysis, right? Communication systems, you name it, you will find linear equations everywhere. Okay, so this is just to motivate you that don't think this module as irrelevant, first of all, and second, easy. Okay, so let's begin. Right, so this is something you are all familiar with, linear equations in 2 variables, in 3 variables. The form in which we will study these equations in this course will be written as a matrix. Okay, so 2 linear equations in 2 variables will now be rewritten in this way. Okay, so if I take the first row, that will be 2x plus 3y is 5, and the second is x minus 5y is 10. Okay. So is everybody aware of this? The matrix form of linear equations?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Great. And the linear system which had 3 equations in 3 variables will now be represented in this way. And in general, okay, so as I told you, we are now going to up the scale, not just 3 by 3, but a much larger system. And in general, you will be able to write this matrix A as an m by n matrix, and all these numbers in the matrix will, for now, be only real numbers. Okay, so a matrix of size m rows, first row, second row, nth row, and n columns, which contains only real numbers, will be an element of the set R m cross n. Okay, so that's another small generalization. Perhaps till now we have only looked at 3 equations in 3 variables, or basically n equations in n variables. We will also now look at m equations in n variables. Okay, so this matrix A need not be square in general, and the number of rows and number of columns could be basically any number that you can come up with. The unknowns will be written as a column vector whose entries would be x1 to xn, and in general we will denote the unknown by variables like x, y, z, things like that. And the right hand side matrix, right, it has m numbers or n entries. Okay. The entries themselves will be indexed by these integers p1, p2 to pn. Okay, I hope it's easy to follow till now. Okay, before we see how to solve it or how to answer the question, right, that when does the solution exist, etc., let's try to get a geometric interpretation of these systems of equations. Okay, so this 2 by 2 system that we saw is just rewritten here. If I have to interpret this system of equations geometrically, what would be the interpretation?
Two lines.
2
Intersect.
lines. So since there are 2 variables, we will be looking at the set R square, which is basically, as far as geometry is concerned, it's your xy plane. Okay, and what are the equations? 2x plus 3y equals 5. How do I draw this line? I hope all of you agree this is an equation of a line. So give me 2 points through which the line passes.
5 by 2,
1
0.
It's again 5 by 2.
0 and 0, 5 by 3.
has 1 comma 1.
This and
0,
1
5 by 3.
so 5 by 3 will be a little difficult. So
1 comma
1 comma 1. So the line is about the second line. Minus 5 by 10.
10 comma 0 and 0 comma minus 2.
0 comma minus 2. Something else which is slightly easier for me. 5
5 comma minus
5 comma minus 1. It's a second one, line 2. What are we trying to find? We are trying to find values of x and y that satisfy both equations. Okay, what does it mean for x and y to satisfy this one equation? It means that the point x comma y belongs to line 1, and you also want the same point to belong to line 2. So geometrically, what you are doing when you are solving this is you're trying to find the point of intersection. Okay, so can anybody find the point of intersection? It's the point of intersection, assuming all of you know how to solve a 2 by 2 system using any method you wish, of course. Okay, maybe you can do this yourself later on. Okay, but perhaps till now, I don't know, I'm assuming that you have only seen 2 by 2 systems where the two lines intersect in a point. With this geometric interpretation, that when you're solving this linear system of equations, you're actually finding the point of intersection between these two lines. So when I change the line, I'm changing the equation, right? So what are all possibilities as far as geometry is concerned for two lines in R2? The question understood?
yes.
In other words, is it always necessary that two lines in the xy plane always intersect?
No.
No.
Parallel line doesn't it?
Parallel lines.
And so when the two lines are coincident on each other.
And when two lines are diverging.
Diverging, what does that mean? So okay, let us first look at this case. Let's say your 2 by 2 system of equation geometrically corresponds to this picture. What would be the solution?
No solution.
No solution.
No solution, right? is coincident lines. Okay.
Infinitely many.
Line 1 is the same as line 2, right? So line 1 and line 2 are the same, but would the equations also have to be the same?
Yes.
Sir,
No,
one
sir.
equation will be a multiple of another equation.
Means it will not.
So 2x plus 3y equals 5. If this is one equation of, and let's say this is the equation of line 1, then it could be, for
4x plus
example,
6y.
4x plus 6y equals 10, right? This would be the equation of line 2, but line 1 and line 2 are the same. So it is in some sense many to one map. Okay? There could be many equations for the same line. And if that happens, we have
Infinite.
multiple solutions, and multiple in the sense that there will be infinitely many solutions. Not two, not three, infinitely many. Okay? So that's the second case. Anything else? Is it possible?
One solution.
Sorry, one solution. So that is
Unique.
this. Right. So what I'm trying to express here is, when you interpret these equations using geometry, you get a clearer idea of what you are doing when you are trying to solve this and how to interpret the system of equations. Okay. In this case, it is very easy. 2 by 2 system, I mean, there's no issues, right? But you can see when you go into geometry, you have a better understanding of not just this given system of equations, but in general, what can happen. Okay? Is there any other scenario that is possible here?
No, sir.
Okay. Then let's look at a 3 by 3 system. How do I interpret this?
Planes.
Planes. Okay. So let's say I give you this equation: ax plus by plus cz equals b. Then
Then it will form a plane with normal as AI cap, BJ cap, and CK cap.
x, y, z. Will it pass through the origin?
No.
No.
Only if D is 0.
Leave
Only
these.
if D is 0.
Normal to the plane. Yeah. To be A, B, C, right? Why should I mean, what is it that gives me this interpretation that the vector ABC is normal to the plane? Well, this plane is this, why should ABC be normal to the plane?
So dot product 0 with any line on the plane.
Okay. Right. So all of you are aware of that? X1,
Yes.
Y1, Z1, and X2, Y2, Z2. Right. They belong to the plane B. Let's call it B1. Then the dot product of X vector ABC with X1, X2, Y1, Y2, Z2, ABC. Okay, which is why we can interpret this as the normal. Fine. Right. So what are the possibilities? Like we tried to interpret all possibilities for a 2 by 2 system. What can we have for a 3 by 3 system?
Intersecting planes.
A line.
So first possibility,
Infinitely many solutions. Line.
Intersecting planes.
intersecting in what?
Sir, there is a line of intersection between two planes.
But there are 3 planes, right? 3 variables, 3 equations. Let's call them given. Then
All planes
Three
can be
planes
parallel.
may
once again,
Skew planes.
what does that mean? See, when we are trying to answer the question with respect to solving this 3 by 3 system of equations. Okay, so by solving, I hope by now you all realize that we are basically trying to find the intersection point of the 3 planes. Right? So what are the possibilities?
they can
They are
intersect
intersect in
to
one
get a
line.
unique point.
Okay, let's first take this case. Let's some point Q in R. Right? So when can this happen? This and this. And this. Line. I'm not making any elaborate diagrams here, but I hope you get the idea. In this case, you have a unique solution. What else? What is the other possibility?
Intersection will be a line.
Intersection would be a line. When can that happen? Be an example.
When two planes are incident.
When 2 planes are
Two
Incident.
planes are parallel.
incident. Achha. Parallel or incident? These are 2 different things.
Incident.
Incident.
Otherwise, it also can happen when all three planes have common line,
All 3 planes have.
but no one are incident.
Okay. Yeah, as well. So, think of it as So given one plane, I'm rotating the plane by two different angles to get two more planes. Okay, so that is this picture. This is again the same scenario. Okay, so no two planes are coincident, but they can still intersect in a line. And this would of course mean multiple solutions. Multiple again in the sense that infinitely many solutions. Any other scenario?
No
All
Planes
all
are
three
parallel
planes
All
are
and
parallel.
one is
planes are parallel.
perpendicular.
One at a time?
Two planes are parallel and one is perpendicular to them.
So in that case, what would be the intersection set?
Line.
Null set.
Null.
Null or line?
Null.
null.
Null set.
Parallel? What else? No solution.
When all three planes are parallel.
All
In
three.
that case also no solution.
Any other case where you have no solutions?
The three planes form a triangle.
Good. Apologize for my drawing. I hope you will like. Anything else?
All three planes are incident.
Principle, nothing to draw.
Sir, when two planes are parallel and other plane is at an angle.
Just so multiple solutions. Yes, two planes are parallel, third plane can be anywhere, it doesn't really matter. Right? Solutions?
There is no solution here.
Okay, so again, the idea behind this exercise is to give you a more visual feeling behind what are the possibilities that you can get while attempting a 3 by 3 system of equations. Okay, are you all already familiar with all of this?
Yes, sir.
Oh, then let's move on to another interpretation of linear systems of equations, and let's start by a 2 by 2 system. And again, in case I'm just repeating what all of you know, please feel free to let me know so that we can speed it up, because in principle, whatever is the curriculum prescribed, we will not be able to achieve it. But again, I'm not worried about that. If whatever I'm doing at whatever speed is helping some of you, then we'll continue with the same. But if I'm just repeating stuff that you already know, please let me know. Okay, so this is your ax equals b. I can rewrite this in a slightly different way. Okay, the way is x is some scalar or some number that I have to determine so that when x is multiplied to the first column, which is written here as a column matrix 2 1, plus y is another variable which is going to be a real number that is to be determined, times the second column vector 3 minus 5 should be equal to the right hand side column vector 5 comma 10. Okay, and when I'm writing this, right, I have yet not defined what does this mean. Okay, so when I'm writing this, I am by this operation between x and this vector, I mean this. Okay, remember this is something that you may already know, but again, from the point of view of abstract math or mathematics proper, remember you must define what this means. Okay, this is not a very natural operation in the sense that both are not real numbers, and both of them are of a very different kind. One is just one real number, the second is a couple of real numbers. Okay, so you must first define it. What do I mean by this? Definition here is this: x into column matrix that contains a tuple, let's say AB, is defined in this way. Okay, similarly, this plus. Okay, what does this plus mean? Why do I need to define this? Because the arguments over which this is going to operate, it is not just ordinary two real numbers. Okay, both of these operands are matrices, 2 by 1 matrices. Okay, so this is where I am defining how to add two matrices. And if you carefully take a look at this definition, is in some sense a source of confusion. This plus that I have written on the left hand side, and I'm using the same notation on the right hand side here, right? So I cannot use something that I'm defining in its own definition in principle. Okay, so the left hand side symbol plus and the right hand side symbol plus are two different things. Okay, what is the difference? Can anybody figure it out? It's not very difficult. So what is the right hand side plus?
It is an integer addition.
Addition of real
That is a
numbers.
Not
matrix.
integer addition. Addition in R. Okay.
Left
Left hand
is
side,
matrix.
Matrix addition.
right? Addition in R2. Okay, so just to connect across courses, all of you have done object-oriented programming, I believe, right?
Yes, sir.
There is this concept called operator overloading.
Yes.
So this is in principle the same thing. The same symbol is being used to define addition between a different class of objects. If I'm right, I'm not very good at object-oriented programming, but I believe that is roughly what we are doing over here. Is that right? Makes sense? Take silence to mean that basic. Okay, but is this clear? I can rewrite this system of equations in this way.
Yes.
Yes, sir.
Yes, sir.
So what is
Yes,
it
sir.
that we are trying to do when we are trying to solve this system of equations? We have two fixed vectors, right? 2, 1 and 3 minus 5. Okay, so maybe let me draw this picture here. 1. Okay. What is the third vector given? The right hand side vector is 5, 10. Choice. Okay. So 5, 10, comma 1, 3, comma minus 5. Now, what does it geometrically mean in this case to solve this system of equations? See,
We have
you have
to
to find
scale.
x. Yes. Go ahead.
We
Go
have to,
ahead.
s- we have to scale these vectors 2, comma 1 and minus 3, comma 5 with some constant so that their vector addition gives this.
Right. So when we scale this vector to 1, geometrically, where will the point lie?
On that line
On
containing
that
On
the
that line.
line passing through the origin and the point 2, 1, right? Why? Because that is the way we have defined the multiplication of a real number with a vector. Okay, and similarly, if I multiply a scalar with the number with the tuple 3 comma minus 5, it will always lie on this straight line. Right? So as note your name, but as we rightly pointed out, all we have to do is find appropriate scalings of these vectors 2, 1, 3, minus 5 such that the addition of these scaled tuples and give you this point 5 comma 10. Okay, so this is sort of the second geometric interpretation behind a linear system of equations, and of course we are looking at how did we obtain these individual vectors. These are obtained by looking at the columns of this matrix A, and which is why this is called, or this geometric picture that I drew is what is called the column picture or the column interpretation. Advantage of the column picture is compared to the row picture we could sort of draw only in 3 dimensions. Extending the interpretation to further dimension is slightly difficult. Here also it is a little difficult but easier than the previous case. So extending it to an m by n system of linear equations, which means that I have m linear equations in n variables. Okay, rewriting this ax equals b in this form, I'm looking for a scalar x1 which when multiplied to the first column vector added with multiplication of this real number x2 with the second column vector, so on and so forth, xn with the nth column vector gives me the given right hand side vector. Okay, here also when I'm writing this, I need to define what is this dot and what is this plus. Okay, so I'm defining it at once. x1 dot this column vector plus xj dot this column vector is defined in this way. Okay, and again, please note the plus on the right hand side is addition of real numbers. The plus on the left hand side is adding 2 columns. This particular operation is what is called linear combination of these 2 column vectors. And since I don't want to keep on writing matrices, I'm going to introduce notations here. A star I. What does that mean? A star I refers to the ith column vector of my matrix A, written as column vectors. Makes sense? Ith column vector of matrix A star I. Okay, so the row index can be anything. It's a variable, but the column index is fixed to I. Therefore, A star I denotes the ith column vector of the matrix A. Okay, is the notation clear?
Yes, sir.
Okay. So, this case also, what we are trying to do is we are trying to find these scaling numbers, right? With how much should we scale this vector, this column vector? How much should we scale the second column vector, so on and so forth, such that when I add all these scaled vectors, I get the right hand side vector B. That is the way to interpret a general linear system of equations with m equations and n variables. So a question, with this interpretation, for a general system, by general I mean the matrix A is of size m by n. Okay, the right hand side vector of course is in Rn. So when does an x exist? Can you interpret this question using the column picture?
Sorry, sir. Can you repeat the last?
Sure. So for this general linear system of equations Ax equal to B, right? I'm giving you a matrix A, I'm giving you the right hand side vector B. My question is, under this interpretation that we are trying to find a linear combination of columns of A that gives me B, what is the answer to this question, that when does the solution to this system exist?
M is greater than or equal to N.
No. M and N can be anything. So there are no conditions on what is M, what is N.
All the points should be on different line.
All the points should be on different line. Otherwise, you think the solution will not exist?
Determinant of A should not equal to 0.
See, I'm saying M and N can be anything.
Okay.
So if M and N are not equal, determinant is not defined, right?
Yes, yes.
But even in that case, do you think the solution will not exist?
The inverse of A should.
So, but if A is not a square matrix, will the inverse exist? Try to interpret this thing. When we are trying to solve Ax equal to B, what we are trying to do is we are trying to find these scaling factors, x1, x2, so on and so forth, xn, such that the addition of these n vectors gives me the right hand side vector B. So when do you think the solution to Ax equal to B will exist?
When A inverse exists.
No. See, A may not even be a square matrix. If A is not a square matrix, A will not have an inverse, right? Do you want me to give an example of a matrix A which does not have an inverse, but still Ax equal to B, the solution exists?
Yes, sir.
Okay, very easy example. You might say that I'm cheating. This is my A, this is my B. What is X?
2.
2. And can see that A is not invertible, right?
Yes, sir.
Okay, so once again, so this is what I'm trying to emphasize, that by now probably you are hardwired to this answer, that in order to solve, or the solution to Ax equal to B is A inverse into B. That is incorrect. Incorrect.
Sir, we have to answer that solution exists or not. We don't care about one solution or
Yes,
multiple.
exactly. When does a solution exist? Right? That is the question.
When all the scaling factors are same.
Why should all scaling factors be same? Chalo, let me give you an example of that. Again, a very tough, say I'm cheating here as well. What is X and Y? What is the solution?
One, two.
1, 2. So the scaling factors are different. See, what is the left hand side? See, the matrix A is given, the right hand side vector B is given. Okay, so if the matrix A is given, I have all its n column vectors given to me.
Yes, sir. Yes, sir.
Then x1, x2 to xn is what I am trying to find, right? And what I am doing on the left hand side is nothing but I am doing a linear combination of these n column vectors. See, I've defined linear combination of two vectors. Using this definition, you can define linear combination of n column vectors also, right?
Yes.
Is it clear to everyone? I have defined over here how to do a linear combination, or what is meant by a linear combination of two vectors. But if you know how to do linear combination of two vectors, you also know how to do a linear combination of three vectors, four vectors, so on and so forth for any finite number n. So if you look at Ax equal to B, all you're doing on the left hand side is you're trying to find a linear combination of n column vectors. And what is special about that linear combination? You just want that linear combination to give you the right hand side vector. Agreed?
Yes, sir.
Yes.
So then when can the solution exist? The
Sir,
condition is on B.
Sir, when A star I and A star J are same, but Bi is not equal to Bj, so solution will not exist. In all other cases, solution will exist.
No. Once again,
when A star I and A star J are same, I not equal to J.
Okay.
And Bi is not equal to Bj, then solution will not exist. Otherwise,
Oh,
solution
just a
will...
minute, just a minute. I'll give you an example. 1, 2, 1, 2, x equals, and Bi?
Bi not equal to Bj.
Then you are saying solution will not exist.
Yes.
So this is an counter example to what you are saying, right? What is the solution?
One.
Equal to 1.
Sorry?
1, 1.
1, 1.
Yes. Okay. But so another condition on B, that Bi not equal to Kbj.
Okay, let me give you, so Bi not equal to,
means they are not linearly dependent.
No, but if you take any two numbers, you will always be able to multiply the first number and get the second number, right?
Yes.
So then for any B you will not get solution. Is that what you
A
mean?
star I is not linearly dependent on A star J.
Please once again, you have not defined linear dependence and independence. So I don't want to hear that phrase,
So
even if
means
you are
A
aware.
star I is A star I times some real number K not
Mhm.
equal to A star J.
But
Like
this is an example where it is, but still the solution is existing.
Sir, the solution will exist when all the BIs can be written as the same linear combination of
What do
the
you
A
mean
star
by
I.
same linear combination?
Sir, means the scaling factors are the same.
Scaling factors are the same, but
It's the coefficient. Means suppose linear combination is
here is this. I mean, take this example number 2. Here the scaling factors are different, right? And there is a solution, isn't it?
sir, means here means suppose linear combination of two real numbers is here I am saying about linear combination of two real numbers. Suppose x and y are real numbers, then the linear combination is ax plus by. So I am saying about that multiplying coefficients.
So what are you saying? The linear combination of
Means all the BIs can be obtained by same linear combination of all the uh, A star I and A star I's. Yes.
and okay. Since I'm out of time, let me give you the answer. Or do you want to try this yourselves?
So we will try.
Okay.
Sir, when B is linear combination on columns of A.
So that is the interpretation, right? When I ask you to solve Ax equal to B, you're just trying to find some linear combination of the columns of A so that you get B, isn't it?
Yes.
So then,
yes.
I mean, you are very close to the answer. When will a solution to X equal to B exist?
Sir, when it is closed,
What is closed?
means Rn, the linear combination of Rn belongs to Rmn.
See, that will always happen, right? Why? Although we did not prove it over here, you can see on I have defined linear combination in this way, right? This equation. Now, if you look at each entry of the right hand side matrix, it is nothing but multiplication of two real numbers and addition of two real numbers, right?
Yes, sir.
So therefore, each entry of this matrix on the right will be a real number.
Yes.
So therefore, this entire thing has to be in Rn. So it is closed, right?
Yes.
Okay, but still we can come across cases where the solution does not exist. Okay, we are very near the answer. Let me give you the answer then. The solution to X equal to B exists if and only if the right hand side vector B belongs to the set that contains all possible linear combinations of columns of A. Does it make sense?
Yes.
See, once again, let me explain this. So, if I pick particular real numbers for x1, x2 to xn, I'm going to get one linear combination of columns of A, right?
Yes, sir.
If that linear combination is not equal to B, then that choice of x1 to xn is not a solution. But you can see that there is no constraint put on x1, x2 to xn apart from that they should be real numbers. So if I try all possibilities for x1 to xn, I'm going to get all linear combinations of columns of A, and that's going to be a set, right? Does that make sense? So if I collect this set of all possible linear combinations and then I try to see whether the right hand side vector b belongs to this set or not. If it does, then irrespective of whether I can find a solution or not, but the solution will exist, right? The question is, will the solution exist, not how to find the solution or whether there are infinitely many solutions or not. The question is, does the solution exist? The answer to that question is, you form the set that contains all possible linear combinations of columns of A and see whether B belongs to that set or not. If it does, whether you can compute the solution or not, the solution will exist. If B is not in that set, surely you cannot do anything to find the solution because the solution does not exist. Does it make sense?
But sir, suppose.
Yes, sir, but there will be infinitely many linear
I
combinations.
don't care. The question is whether the solution exists or not, as I said, right? I'm not worried about whether the solution is unique or not. That is something we'll take up in the next class. For me, what is important is whether I can solve this or not.
But sir, if there is one value of x1, x2, x up to xn for b1, let's say, and
Then that, see, what are we trying to do? We are trying to find one value for x1, x2 to xn such that this, what is the left hand side going to be? It's also going to be a n by 1 matrix.
Yes, sir.
The right hand side, sorry, m by 1, not n by 1.
M by 1, yeah, sorry.
Right, and the right hand side is also m by 1.
Yes.
When do we say two matrices are equal?
When corresponding elements are equal.
Each and every corresponding element has to be equal. Only then these matrix is equal.
Yes, sir.
So by a solution to x equal to b, we mean that such scale numbers x1 to xn such that all these equations are satisfied. If one entry corresponds, first entry on this side corresponds to b1, but the second does not, then that cannot be a solution.
Yes, sir.
Okay?
Yes, sir.
Okay, so which is why I'm saying if this entire matrix or this entire vector b, right, if that belongs to this set of all possible linear combinations, then the solution will exist, right?
Yes, sir.
How can we check whether it belongs to the set or not?
Yeah,
Yes.
so that is something we are going to look at in the next class.
Sir, because that all the set of all linear combination will be an infinite.
Infinite, yes, agreed. But the only question we are trying to answer is, does it exist or not? How, that's a different thing. How are we going to find the solution? That is going to come up later.
Okay, sir. Sir, I am having a question. Sir, here the m-dimensional column vector, is it interpreted as a point in the m-dimensional space or a vector?
Yes, yes. So you can interpret it as a point, but it also is a vector. Right. There is a small typo here. I can see that now. All of these column vectors are m-dimensional. Okay. Sorry. Yes, you can make that assumption, association. Sorry, not assumption. The same that we did over here. You can interpret these as these, let's say AB, as x and y coordinates of a point. You can also interpret this as a vector from 0 to this point AB.
Yes, then that will be a position vector, right? Position vector of this point.
Yes.
Yes, sir. I was just having that confusion.
Okay. Okay, but when you interpret something as a vector, remember the vector has to start from the origin. I mean, something like this does not make sense.
Yes, sir. Yes, sir.
Is that okay?
Yes, sir.
So I hope this answer is convincing. If I'm only worried about whether solution exists or not, I only need to look at whether B belongs to the set of all possible linear combinations of A or not. Okay, so that is clear. We'll stop for today. Once again, I apologize for coming in a little late, and yeah, I hope it will not, never happen again. Sorry once again. Okay, see you guys on Tuesday.
Hello, sir. I have a small doubt. Can you
Go ahead.
say about what we have to do in project? And
What you have to do, so we have given you a little description. You are supposed to study that particular topic from the perspective of linear algebra and groups, right? Find out everything as far as you can about it, and whether you sort of study applications of it or not is something that we are not very worried about. Okay,
okay.
so you must demonstrate a complete understanding of that topic from the perspective of this course. You can go a little beyond the course also wherever it is possible, and then you are supposed to write a report and present to us.
So, the report should be in form of LaTeX or some other.
Yes, I think later.
Sir,
Yes.
in my group, sir, 2 people have already left. So what should we do for that?
And
Like,
how many of you are there?
right now, currently 8 are only there.
8 is also a big enough number, isn't it?
Yes, sir. I just wanted to inform that, like.
Sure. So if it goes below 8 in the next couple of days, I will reassign something. But otherwise, you can go ahead with 8.
Okay, sir.
Any other questions?
Sir, what is deadline of this project?
So take it as of now as 1st of December, roughly.